Hi, everyone. Welcome to the Sparlin Experts webinar on basic refrigeration cycle. We're using a new webinar delivery program today, so there might be a few glitches in the presentation. We're doing our best to understand all of the features of this platform on our first trial run. During the course of the webinar, we may solicit input in the form of polls. These polls automatically close in 60 seconds, so we encourage you to input your answers quickly to avoid being shut out of the voting. Also, the chat function will allow you to answer or ask questions from our presenter. Our moderator, Dennis, is on hand to review the various questions and post them for the host to address. These questions will be visible on your screen when they're activated. Also, attendees will be receiving a follow-up in the form of an email, which will contain this presentation and some links to other materials that Paul is using in their presentation. So before we dive in, let me introduce our speaker. Paul Chambers is an applications engineer with an emphasis on training. Paul earned his Bachelor of Science in Engineering Technology from Pittsburgh State University in Kansas, where he dual majored in mechanical engineering technology and automotive technology. So all right, let's get started. Paul, let you take it away.
Absolutely. Thank you for the introduction. So I'll hit present now, and hopefully you can all see these slides. Let me know if you can't. Before we go, I'm going to mention, so as John said, I started at Pittsburgh State. I studied automotive. I understood this refrigeration cycle from working on cars. It's the same basic components, and we're going to talk about that, the basics of refrigeration. If I could understand it when working there, and it's still applied here at Sporlan working on large rack systems, you can get the grasp here, and it will help you all over. So this is our experts webinar, and they have dubbed me that. I will not claim that for myself, but thank you for everyone who has. We'll go on to our material. So what is refrigeration? Whether that be an air conditioning system, refrigeration, or a heat pump, all of those devices, all of those systems are going to come down to being the same method of work, and it's that they all move heat from one location to another. It's usually, and we're going to talk about specifically the vapor compression cycle. You can achieve refrigeration with other methods. You can just have a big block of ice. That would be refrigeration, old ice boxes. But when we're talking about the vapor compression cycle, it can be used in air conditioning, refrigerations, and heat pumps. And we'll talk about how those all utilize the equipment in the same way. So if we're going to move heat from one to another, we'll talk about the basics of how will you move heat. Well, you're going to need a path. So how are you going to end up to move the heat on? So not just the piping, but also something inside to put the heat into and take it out of. So that will be our piping and refrigerant. That would be one thing. We have a path now for heat to move on. If you wanted to do refrigeration, you'd also have to keep that path moving, actually make the march go around the circle. Well, that would be your compressor. And then you would need a place for the heat to get in and out of the path. Those are called heat exchangers. In air conditioning, we're going to call them a evaporator and a condenser. They might change name a little bit depending on application, but the heat exchanger will always be a apropos term to use. You can always use that. And then lastly, you're going to have something on a vapor compression cycle to encourage the exchange of heat. And so in this one, it's the only one that's not super obvious. It's going to be an expansion device. Everything else should be pretty obvious. You need a pipe to go around. Compressors, sometimes you'll hear people call them pumps. Those are just going to compress, they're going to move, they're going to keep it, from low to high, they're going to move that system around. You want something to exchange the heat, and the expansion device is the only one. We'll get into why that's needed. So those are the four main components that you'll hear. Sometimes you'll hear the four main components being the expansion, compressor, evaporator, condenser. Sometimes, they say 5 or 6 components because you need the piping, the refrigerant. I've put them here. That is what you would need. And so we'll go into that first one, the refrigerant. Well, like I said, it's something that you can put heat in and out of. So heat is energy, and it can be stored inside of any substance. If you have a rock in a campfire and you take it out, it's still hot. That rock has stored heat. Heat can also, when inside a substance, can be affected by pressure change. So that will affect the phase change. So we talk about water boils at 212 degrees. Well, that's when you're here, at sea level. If you're in Colorado up on a mountain camping and you want to make a pack of ramen, I can tell you from experience, it does actually boil at a lower temperature. It changes how you cook your food. So that's just a fun fact that does affect a little bit. And then we'll talk about how you choose a refrigerant. I've listed out a few of them here. So each material has its own unique boiling point. Most often we talk about R17. And I put these not because I think it's kind of funny, we have these different list of names, and they can look complicated, especially when you start to get into refrigerants. It's just some complicated chemical. Well, we can start here. Dihydrogen monoxide, that's H2O. Water also has an R number, a refrigeration number, R718, and we can see that boils at 212. That doesn't change. The same math works the same whenever we get to other chemicals, other refrigerants. You could talk about carbon dioxide. We're still familiar with that. It's, when I breathe out, that's carbon dioxide. Well, it also has an R number, refrigerant, and we're seeing that now used in refrigeration. It's R744. It's going to boil different than water. It boils at -109. One thing you can take from that is if I got down to below -109 degrees here in this room and I had some carbon dioxide, it would condense into a liquid. Or if you imagine all that carbon dioxide and I squish it down, pressurize it, I could also make it into a liquid. That's where we get back to that heat and pressure or have a relationship on when things condense and evaporate. And then now these last two are not going to be ones we're familiar with out in the real normal world. H2O, CO2, we're familiar with those. But I put these in just to show that it's just another chemical chain. It's just another substance. And difluoromethane, what is that? Well, it's R32, and we've actually been seeing it in the industry for a long time. It boils at -61. R454, anytime you see an R400 something, that's going to be a blend of multiple different chemicals, refrigerants. And so that's R32 again, and R1234YF. It's going to boil at -59. So now we get this idea that we have chosen a substance that boils very cold, right? We're boiling below 60 degrees, -60 degrees F. Harkening back to when I learned all of this in automotive, the one we were working on back then was R12, and the way I always remembered that one was it boils at -21. Inverse of 12 is flip the numbers. I'm dyslexic. Flip the numbers 12. It's 21. Go negative because it boils really, really cold. Same stuff all the time. So now we know we could actually choose something that's boiling off. It could be a liquid, but usually we're going to say it's a vapor. And we could map it out a little bit too. That mapping is going to be called the pressure-enthalpy diagram. You might have seen this before. You might have not understood it. Well, we can understand it pretty easily. On the left, we've got pressure. On the bottom, we have enthalpy. Pressure is a term that we've probably all heard of before, and we talked about it earlier. It's squishing things down. PSI-A is what is listed there. PSI, pound per square inch. You've filled up the air in your tire before. You've probably been around something that's pressurized. If you see an A on it, all it means is absolute. So earlier I talked about where these boil at sea level. Well, absolute means right here where I'm sitting in Washington, Missouri, we have 14.7-ish PSI just in the air around us. That's all the air above me pushing down on me right now is creating about 14.7 PSI of air, and I don't even, we don't notice it. It doesn't register. If I had a gauge in my hand, it wouldn't register. It would read out 0 PSI. That's what I'm going to use to measure the pressure in my bike tire. And that's why we have another one called PSIG. That's pressure gauge. Gauge pressure is what it's accounting for the atmospheric pressure, the absolute pressure, and it zeroes out. So that's what the scale we have on the left. On the bottom is enthalpy. You might not have heard of that before, but it's just stored heat. Heat is energy. It can be stored in a substance. We talked about that earlier, and we can measure that. We measure it in something called BTU per pound. So per pound means per mass of refrigerant. We're going to have a BTU, and a BTU is just a British thermal unit. So the amount of heat needed to raise water 1 degree F. As you can imagine, 1 pound of water 1 degree F. So as you can imagine, that would be a consistent amount of heat that you put into something. That consistent amount of heat per pound is the amount of stored energy inside something. And you can map it out. We get this, pressure versus enthalpy. I don't know if I can use a laser or not. I don't think so. Point at stuff. So we have that pressure versus enthalpy. And then we have a curve across the middle that one of the guys I was working with, I prepped a little bit, explained some of this to some guys who hadn't heard of refrigeration before, some guys in marketing and stuff like that. I say heard of, they weren't familiar with the nomenclature. And one of them said, yeah, the jelly bean curve. And so what that fine gentleman will refer to as the jelly bean curve, that curve up in the middle, that dome, pressure enthalpy dome, is actually just a map of the states of the refrigerant. So whether it's a liquid or a vapor, or maybe somewhere in between, it's kind of in the process of boiling off. We can talk about where those actually land now. So here I'm going to say understanding the curve. So what does the curve actually define? We said it defines the state that the refrigerant is in. Well, over on the left, we have something called a subcooled liquid. When we have water sitting on our table, that is a subcooled liquid. It is liquid and it is degrees away from boiling, right? It is pressurized and it is degrees away. When we have a CO2, right? I breathe out CO2. That is superheated vapor. It is very far away from being a liquid. But as we lower the pressure, or as we can go back and forth. As we introduce and remove heat, we can go back and forth. The way I've always tried to describe superheat, aside from, because we can imagine vapor being vapor. Most of the time we see CO2, it is vapor. The other way you can imagine it is if you were to take something past the boiling point. So if you had water and you take it to 212 degrees, it boils, capture that steam, take it even farther above 212, that would be then superheated water, superheated R718. Subcooling is the exact opposite. You could take it back and go across. You might hear people talk about quality of the refrigerant. And so when it's inside the dome, it's not one or the other, it's a mixture. And so over on the left, I really thought I'd have a laser pointer in here. Over on the left, where it says saturation line, that line is where it becomes a saturated liquid. That would be a quality of 0. Because 0 to 1 inside the dome. So over on the other side, where we see those droplets forming, that will be a quality of 1. Still another saturation line. We have the saturated liquid line, saturated vapor line. We have bubbles on the left because we'll refer to that as the bubble point. And you'd use the bubble point if you're calculating subcooling. You use the dew point is where it's the liquids are forming on the right. The droplets, that would be where you calculate your superheat. I acknowledge that was, and we have one more slide where it's a little bit, it's a little bit odd and a little bit in the weeds, but we'll have one more. And forgive me, here's where we're actually going to look at the full pH diagram. Now it's no longer just a few colors. And we're not going to dwell too much on this because we could spend too much time, and it's not actually needed to understand this fully. But I want you to understand that refrigeration is a very simple system, uses complex math behind the workings of it, but you don't need to understand all of it. So on here, we can see that the main point that we want to see and understand is that our pressure or our temperature, with those horizontal lines inside the dome, temperature stays the same across. That's all you need to understand from this. We map a lot of other stuff on this. And every now and again, you might see something about refrigeration that seems daunting. Well, you could have another conversation like this and probably understand it pretty quickly. But the main point on this one that I'm going to make right now is just that temperature stays the same going across. And you can imagine that too, that when you boil water, you can get it up, you put it on your stove, let's say you have a thermometer in there, you get to 212, right? You come up, it comes out of your faucet, it's 70 degrees, whatever. You bring it up 100, 150, 212, it starts to boil, and it stays there at 212. Now you've entered into the dome on the left side. You've entered into the dome from the subcooled liquid. You've come in and you've started to reach that bubble point where it starts to boil. And that water will stay at 212 degrees. I'm going to venture to guess that none of you have ever seen a pot of water above 212, a pot of liquid water above 212. Because what happens is if you've ever put a thermometer in there, it stays at 212 degrees as it boils across. And that's when you come out of the dome on the right side. That's where we talk about the dew point. So now it's boiled off, it's become steam, and that's when you could actually have steam above 212 degrees, but liquid water not. So that's the only point we really want to drill in, is that inside the dome, the temperature is static. left to right. So apologies for all the oddities of choosing the refrigerant. It's helpful to understand what we're working with inside the system. But now we can talk about how you'd actually build that system out. We talked about the components, and now we'll put them in order. So we said that we'd have a path to move the heat, and that's the piping refrigerant. So we have these black lines going in a nice little rectangle here. We have a device to keep that path moving. So I choose now. You could draw this in a different way, and hopefully by the end of this presentation, you'll see why I draw it the way I draw it. I put that compressor over on the right, going up. So we have a compressor on the right going up. It's going to take a low pressure refrigerant in on the bottom and push it out the top. We need devices to get heat on and off the path. Those are called the evaporator and condenser. So we'll put the condenser after the compressor, and then we'll have the expansion device, and we'll get back to that evaporator. The expansion device is there to encourage heat transfer. We'll talk a little bit more about exactly how that works. But now we've actually built out. Earlier we said those are the components you'd need if you wanted to move heat from one place to another. Well, here's the order you put them in. We can change that same graphic, same order, but now it has icons showing a condenser, a compressor, evaporator, expansion device. So we can talk about specifically how each component works. The compressor raises the pressure and adds a little bit of heat. The adding heat isn't necessary, but it's something that it's good to know that it does that. And it does that because it's doing a lot of work. You got a motor attached to it. It's a hot thing. If you go and grab onto it, you're going to burn yourself while it's running if you grab onto it. So now we can see it adds heat and raises the pressure. An important thing to know about compressors, and I've tried to drill this into people. I've met some people that really want to try the opposite, and it doesn't work well, is it must be vapor entering that compressor. If you think about, and if you worked on cars, you think about, we have liquid hammer happens on cars, it happens on compressors. If you think about taking water and trying to squish it down, you're not going to be able to squish it. But if you had a syringe of air in it, you can squish it down. Think about a basketball outlet. You can compress the air a little bit, right? But you couldn't compress it if it was solid liquid. Well, that's the same thing. So the compressor needs to have a vapor that can come in that can be compressed and brought up. It's going to bring that compressed vapor up to a higher pressure. That higher pressure is now going to be hot. It's going to encourage to condense, so it moves through the condenser. At that point, it's going to reject the heat. So the condenser condenses the refrigerant into a liquid, rejecting heat into the air. So it just takes the heat that was in the refrigerant, puts it out into the air, and condenses down into a liquid. The same way that if you've ever had a nice cold cup of tea and you see liquid coming on the outside, that same thing. It's just condensing the liquid condensing the vapor into a liquid. And in the process, it's, like I said, rejecting heat. Heat goes in, it's putting off heat into the outside air. On an AC system, you'd see this, this is outside your house. That expansion device exists to create a pressure drop. So where I said earlier that you can, that things boil at a lower temperature up in Colorado on a mountain, well, things also boil at a much lower temperature if you can actually drop pressure a lot. Going up from Missouri to Colorado, you might drop a few PSI, maybe. But here, that expansion device is going to drop it more than 100 PSI. So now we drop that pressure, and it's encouraged to boil now. That's what we said, right? It's easier to boil now at a lower temperature when the pressure drops. So that expansion device causes a pressure drop to encourage evaporation, often controlling to a superheat so that it's going to a certain amount above the boiling point. We see that in a TEV is controlling to a superheat. And then your evaporator is going to your refrigerant goes through the evaporator, and that's where the air to evaporate. It says, hey, we're ready to boil. This refrigerant has just dropped in pressure. It's ready to boil. It's ready to, change phase into a vapor, but it needs heat to do that. So it's going to pull heat out of the air. That's the heat that's then going to reject out of the condenser. And it's going to repeat the cycle. So it takes heat out of the air, puts it into the refrigerant, goes through the compressor. Now it's ready to condense because it's at a higher pressure, condenses the condenser, repeats the cycle. And that is the same thing over and over again. That's the same thing whether you're doing a air conditioner, a heat pump, or refrigerator. Originally, if you think about the definition of the word air conditioner, because we just say that now, and a lot of us think it makes the room cold. That's part of it. It's really conditioning the air. That's why we call it an air conditioner. Conditioning meaning it's making it comfortable. There's an ideal temp and humidity. We've all been in a room that is often one or both of those measurements. You've been outside in the like I said, I'm from Missouri. Hot, humid is the opposite of what I find comfortable, but it is what we have all summer, and that's what we're trying to fight. So when we have that evaporator, it's boiling off, it's getting cold, it's removing heat from the air in my house, it's making it colder. It's also getting so cold that water condenses out of the air. So even though the refrigerant is evaporating, the water in the air is condensing, drips down into a drip pan, goes down a condensate line, and now I have conditioned my air to a set temperature and humidity. That's why it's called an air conditioner. I could use the exact same system that we're picturing here, no changes whatsoever, and do a refrigeration system, refrigerator in my house. Now, the main goal is I'm removing heat again. That's still the goal, but rather than from in my house, it's from a set space for the purposes of keeping a space cold or cool. That's really the only goal, or humidity as well. But refrigeration and air conditioning, it's the same thing, usually with different targets, because now it's not for comfort, it's for cold. So, my refrigerator is colder than I want my house to be. My freezer is much colder than I want my house to be, but it's the same system. And then the last one, we hear a heat pump. If you're in the residential market, you might think that it's a more complicated system. But really, when you're talking about a residential heat pump, it's an air conditioning heat pump combo. A heat pump is in by itself just the same technology, but thought of it backwards. It works in the same way, but you think of it in a different way. Because now you're not removing heat from where you want to make a cooler, colder, comfortable place. You're now removing heat from where there might be excess heat, and you're putting where you want to heat something up. So you might see this, you're taking heat out of water, and you're going to, or heat out of the air to heat up water. So there might be heat outside, and you don't mind if you make it colder, and you can put it into your water. That system is actually becoming a lot more common now. And we see that in something called a heat pump water heater. Mandated in the US, we're going to be seeing a lot more heat pump water heaters. And the way those work is you put them in your basement, they take some of the heat out of your basement and put it into your water. I was at a wonderful presentation recently with some people who make those, and everyone's trying to, how do I tie that into my system? It doesn't take a lot of heat out, but it takes enough. It doesn't take a lot of heat to heat up some water. What will raise or lower the temperature of your basement by a couple degrees can drastically change the temperature of your water. So that's why it's an effective method to use the same 4 or 5 component system to remove heat from the air, put it into the water with the evaporator condenser. Now the condenser is the part where you're actually doing the work. The condenser is the part where you would have a refrigerant to water heat exchanger on your condenser, and you're just dumping heat into the water, pulling it out of the air. And it's also why they chose that technology. If you think about your refrigerator, air conditioner, when was the last time you serviced your refrigerator? You have those in your garage, they work 20 years, never break. That same kind of technology can be used and taken advantage of to heat water with the same reliability. So that was the system, these 4 components. I could back up a little bit. When I was in school, learning this for the first time, every morning when I came into class, my teacher demanded I draw these 4 components in a circle, in the square. And I would suggest that if you're new to this, you do this exercise. Every day when you get to work, every day when you start to think about this, draw these out until you have no question about what order they go in. And it shouldn't take long. Most of us, in our class, into the first week, we can nail this out, no problem. And then we can start to look at it with more complication to it, not complication, but with more analyzing spirit. So let's divide it up a little bit and kind of think about where things are. Well, I've just divided this in half now. We have the high side and the low side. And we can see that the compressor, which we said raises the pressure, compresses the refrigerant, raises the pressure, is right on the border of the high and low. The expansion device is right on the border of the high and low side of the system, because the expansion device is a pressure restriction. That's all it does. And you could use here we have pictured a TEV or a TXV, as a lot of people in the industry call it. You could do that with an electric valve. You could do it with a fixed orifice. And that's what, when I started in automotive, that's all it was. It was a very small hole in a tube that caused refrigerant to back up behind it and build up. And so there was all of the molecules were building up here. There's a lot of refrigerant up here, not a lot down here on the downstream. And so high pressure here, can't get through very fast, bottlenecks, right? And so low pressure on the downstream. So however you choose to expand it to cause that pressure drop device, cause the expansion, those are the borders of the high to the low. This is very important if you start to work on refrigeration, because you might hear someone talk about the high side of the system, head pressure, high side, head side. These are going to be just knowing where they are in the system. You can start to find stuff. If someone said high side controls, I can now know it's going to be between your compressor and your expansion device. I don't have to be looking somewhere else in the system. And really, I'm probably going to be controlling, if you're controlling like a high side pressure device, usually you do that upstream of something, right? Because we have a pressure regulating device here. It drops the pressure. The only thing creating pressure is your compressor. So if you're going to drop your pressure, you're going to be between your compressor and your condenser. So knowing how these systems delineate from side to side will affect how you can find things. We can do it again here on the liquid and vapor. So vapor is going to be on your right. We boil as we come out of the evaporator. We come into the compressor, we're still vapor. We compress to a higher pressure, still vapor, go through the condenser into a liquid, and now we're liquid again. Go on the liquid side, we're coming in from the condenser. We now have a full head of liquid, full line of liquid in the pipe, comes into the expansion device, pressure drops, it wants to boil, it goes through the evaporator, it boils, turns into vapor. So now you can know if you have liquid control side, where to look in the system. And the last one, this isn't all true of all, because you might have a package system, you might be doing a heat pump water heater. But if you're doing residential AC, which is where I moved to after my work in automotive, you'd have your inside and your outside, and you'd see it on a split system, something like this. You'd see those condenser compressor, and if you think on everyone else who has air conditioning, you have that has a compressor and a condenser around it. That's the outside of your house. You have two lines coming towards your house for your air conditioning. You have a supply and a return, and then inside your house you have a air handling unit or a furnace combo. You're going to have your expansion device, your evaporator. I don't feel there's too much need to drill into this, but we could put all of those slides together and you would have this diagram. The same that I said before goes for this. If you're learning this and you wanted to be an expert of where to find things, an expert of how to work, how to service and troubleshoot these systems, and this causes you any confusion or pause, I would practice drawing this every morning. You're going to figure out, now if I want to say, well, I have, let's see, an evaporator pressure regulator. I've just chosen a device. Well, I know that it's going to hold pressure up, because like you said, that's all it can do is hold pressure up or down. Well, the expansion device is already making the pressure drop for the evaporator. So now I want to hold pressure up for the evaporator. It's the only way I could regulate the pressure in the evaporator would be to hold it back to a certain pressure. And so between the evaporator and the compressor is where I would find a evaporator pressure regulator. Don't even have to know what it does. If I know those words, know what they mean, you can find them in the system with a drawing like this. Understanding the actual flow and the basic function of each one of these devices, how it evaporates, condenses, raises and lowers pressure, you'll be able to find it. The other reason, earlier I said, why do I write the compressor on the right side with going counterclockwise? Well, when I first learned this, he actually made me draw a compressor on the top going clockwise. It was a guy when I got hired here at Sporland who taught me to draw them counterclockwise. And it's because if I draw them like that, they match up with that pressure enthalpy curve that we looked at earlier. Because remember, we said it has to be vapor on the right? Going into the compressor has to be vapor. Well, here we see that our compressor is on the superheat side, superheated vapor. It's got vapor going in the bottom, vapor coming out the top. The condenser is where we see us crossing through that line again. That same solid temperature, which just rejects heat out and it makes a liquid. We said that our expansion valve, our pressure drop device, would drop the pressure of a liquid. Well, it's over there in the subcooled liquid side. Your evaporator is down there in the dome again, where it's crossing back from liquid to superheat. And so that's why I would say draw it in the counterclockwise with your compressor on the right, is it matches that. We also said that the compressor adds a little bit of heat. So if I were to draw it more realistically, it makes this shape, this kind of trapezoidal shape with one at an angle. Because it comes out, we have superheat coming out of the evaporator, and then it continues to get some heat from the compressor. A few things to be aware if you see someone draw a picture like this, and those eagle-eyed viewers of you might have noticed there's some errors. One is that every line here is an entire component. The compressor is not in the middle of that line. It is the whole line. And the other error that I noticed while making this, and hopefully someone else could catch, is that if you're using a TEV, or TXE as some call it, like I said, you can use those to control to a superheat. It's always creating a pressure drop to make sure you get enough boiling to get to superheat. Well, that bulb of the valve would need to be measuring superheat to say, well, we're going to measure at that pressure-temperature relationship to create superheat. That would mean it would have to be outside the pressure dome. I've worked with some engineers who tried to, so here we have it imaged inside the dome. That would still be a mixture of liquid and vapor. Right, we talked about the quality and how you have a saturated and a liquid and a saturated vapor. Well, it's between those 2 points, it's a mixture. It would not be controlling well. So even though I made this slide, there's still an error in it. Isn't that amazing? Once again, this was the basics. That's the 4 components. This is how it fits in the pressure enthalpy. This is how it raises and moves temperature from one side to the other. Heat goes in on the evaporator, out on the condenser. AC, refrigeration, heat pump, it's all the same. And then we'll go into a little bit of troubleshooting, and then we'll wrap up see if anyone's got some questions. So the first troubleshooting, and I put the diagram over there on the right so that we can actually look at how it would affect each system. I've picked out 4 that we'll go through 4 troubleshooting common issues, things that we see most often in the industry. And the first one is going to be undercharged. We see undercharged a lot for 2 reasons mainly. One is every system leaks. It's not about if it leaks, it's about how much it leaks. And then we also see that you might not have charged it up to begin with. You might have started off, if you're in residential, you might have started off with the factory charge and it wasn't enough because you added more line set, and now you're undercharged. There's not enough refrigerant. So how does that affect the system? How would I know that that's the issue? Well, now I know where to look on things. So my discharge pressure is going to be lower. And that makes sense. I don't have enough refrigerant anywhere in this system. Everything is low. We're talking about that pressure is those molecules of refrigerant back together really tight to condense into a liquid, or in the high side. Well, if I've got low amount of charge, is not enough to stack up, I'm going to have low discharge pressure and low suction pressure as well, because everywhere in the system it's low. I'm going to have low subcooling. That's the 4th point there. Because if I can't hit that high pressure, I can't squish all my refrigerant together. I can't force it to condense into a liquid in the same way. So actually, I'm going to have a lower subcooling number. I'm not going to get as far outside of that pressure enthalpy dome that we saw earlier. And I'm going to have high superheat, because on the same side of it, now I'm going to be I'm going to be low pressure. It's going to want to boil off. And so I'm going to have this high superheat. The valve is basically just going to be all the way open. It's just not working. You're just going to have high superheat. So if you're troubleshooting a system, if you're working out and you go and you have low subcooling, we're talking 2 or 3 degrees of subcooling going into your indoor portion, you have high superheat coming out. Both high and low side pressures look a little bit low. You can suspect a undercharge. Another common issue we're going to see is a restriction of the liquid line. This could be for a few reasons. One is that the expansion device, that'd be the valve, a fixed orifice, is going to be about the smallest point of passage anywhere in your system. Everywhere else is going to be a fairly large pipe, and that is going to be like I said, you want to cause everything to back up. Well, if it's the smallest point of passage in the system, it's also the easiest to clog with debris. When we initiate a system, we start it up for the first time, we've brazed, we've soldered, you might have oxides on the inside of the pipe from not proper purging or something like that. Really easy to clog those. You also might see those same debris and gunk clog up a filter dryer. So we put a filter dryer often in the liquid line to catch that debris, catch any moisture you might have left in the system, because we were very careful when we chose our refrigerant. It had specific properties. Like I said, each one had a different boiling point. Each one's going to have a different map of a pH diagram. We chose a specific refrigerant for a specific reason, so we would know when it boils and when it doesn't. Well, if I start mixing those, it's not going to work well. So if I know I wanted R32 and I put some water in there, well, now it's not going to condense at the same point. It's not going to work. So we have a filter dryer to catch the water, catch any moisture. Not a lot of water, but if there's a little bit of moisture left, if there's some debris left, they can catch that. It could also become clogged and create undue restriction in your liquid line. Well, now I'm robbing my pressure drop. My expansion device is there to create pressure drop, and I'm creating excess pressure drop before I get to my valve. So I'm going to going to have high superheat, because now I'm dropping pressure again at a very low pressure, high superheat. I will also probably see high subcooling as more and more of my refrigerant stacks up on the high side. Now, this is where these last 2 points, I have low suction. That makes sense. I'm dropping my pressure really low. Low discharge is that one can cause a little bit of question, because you'd say, well, if I'm stacking up all my refrigerant on the high side, wouldn't I see high discharge pressure? And it might depend on how the system is laid out, but you might actually see a low discharge, because all that compressor is designed to do on a lot of traditional systems is it's designed to create a fixed pressure differential. You'll hear people refer to the envelope of the compressor, basically how it performs. And they'll be rated for a delta PSI. How much does it take from this to this? Well, if my suction pressure is low, it can't take, it's supposed to be, let's say, 150, and now I'm down here at 90. Well, it can't take 90 and bring it up the same higher pressure that it used to. It's just going to do the same. Let's say if it was 150 to 300, so it's 150 psi across the compressor. Well, now if I drop a lot, it's still going to only be about 150 psi across. So you might actually see a low pressure on the high and low side of the system. Another issue we're going to see a lot is going to be a dirty or low CFM, cubic feet per minute, airflow evaporator. This is where you see the evaporator doing the work. Usually that's a air to refrigerant heat exchanger. It's really easy to just not clean those, right? I was talking with somebody, a friend from church, and he was talking that he had never changed the air filter in his house. Didn't know that was a thing that he had to do. He had lived there for a couple of years and never changed it. He also had a dog, and I can guarantee you that if I had gone into his house and looked at his evaporator inside his air conditioning unit in his house, it would have been caked. It was just, it builds up with all that dirt and debris, and now you can't do work across it, right? We're trying to put heat into the refrigerant across that by blowing air across the pipes, across the fins of the evaporator, and getting heat taken out of the air, put in the refrigerant. Well, if I can't do that, it's not going to do the same work. So we're going to have low superheat. That's the third point there. We'll have low superheat as it's not able to pull the heat out. We're going to have probably hunting hunting is when we see that superheat kind of go back and forth, kind of all over the place. The valve might be in the wrong, basically in the wrong size now, because the evaporator is not doing a lot of work. It's an improperly sized valve. So we'll start there at the evaporator, because that's the part that we have the issue. So we don't have a lot of superheat coming out through the compressor. We have a low suction. That's going to be because we dropped through the evaporator, dropped through the expansion device, boil off, kind of low superheat. And we have low discharge again. We're not doing a lot of work. We're not heating it up. Heat and pressure are related. And then our subcooling will actually be about normal. Our condenser isn't that dirty. It's able to condense back into a liquid, but it just can't really do the work on the evaporator. You'll also see this if the main issue you're going to notice is that you're going to not have a you're not going to have good cooling on your house or in your space. The fourth and final is going to be the opposite of that, your dirty condensers. So you have a cottonwood tree in your backyard, you have leaves, whatever it may be, covering that condenser, and now you can't condense into a liquid. You can't get to that subcooling. Here we're actually going to now see the opposite of what we've seen. Everything's been a low pressure. Everything's kind of taking work off the system. Well, now we still have the same work. We're still dumping heat into it. We're still asking the system to do a lot of work by pulling heat out of the air. But now it's not able to reject that heat because it rejects the heat out of the condenser, right? We learned that. It rejects heat out of the condenser into the outside air or into the water if you're doing a heat pump. Well, if it can't reject the heat now, well, it's going to take heat out of the evaporator, get more heat from the compressor, go to the condenser, it can't get rid of it. Go through the expansion device, it still has more heat. And so that heat is going to keep working harder and harder, build up the heat, build up the pressure, and we're going to see high discharge pressures. We're going to see high suction pressures. We're going to see high superheat, possibly hunting, as it is not able to condense. So even though it's high pressure and you think that's squishing the refrigerant back down into a liquid, well, it can't condense. It's just hot superheated vapor. And for the same reason, we're going to see low subcooling because as it comes to the condenser, it's not able to condense. It's not able to reject the heat out. And so if you're on a system, you're working on it, all your pressures are high, your superheat is really high. It might be hunting, moving around as it's unable to control. Your subcooling's low. Look at your condenser. Is it dirty? Is your condensing fan bad? I was watching a great video from Chris Stevens, and he was working on a system, and one of the fans had gone out. So he was running a little bit high because there was a multi-fan system. So one of the fans had gone out, and it had caused some high pressures and low superheat. Knowing how everything moves through the system, now you can go through and say, well, why would this be that way? I know where to look. I know where to put my gauges if I want to measure high pressure and low pressure. How is that going to affect the system? So the drawings we talked about earlier really helped me understand this as I was learning the system. The last thing, all of these last 4 slides we pulled out, troubleshooting, all came from this slide. So once again, the goal of teaching is to steal things that people gave you that helped you learn. This was one of the all 4 of those were taken off this basic system analysis. Somebody gave this to me when I started here at Sportland. I honestly have no idea where all it goes back to. I'd be curious if anyone recognizes it and says, oh yeah, XYZ company made it. I have no idea who or where it came from. But go through this line by line. Do you understand why is it doing this? Draw out your system next to it on a piece of paper and say, why is my amperage higher on this? Is it doing more work? Is it not able to reject heat? Are you asking the same of the system? These are the basics of refrigeration, that if you can understand why a system would have these reactions, what the 4 components do, you will be a much better troubleshooting, much better all around engineer anywhere in this industry. So that is the end of my slides. I don't know if we have any questions. I don't see any coming up through. If you had any questions in the middle, feel free to ask them now. If not, I'll pass it back over to John.
Great. Thanks a bunch, Paul. That was super interesting. I want to thank everybody for joining us on our webinar today on the refrigeration cycle. I hope you found the information valuable and that you can take a couple of nuggets of wisdom with you on your next service call. Special thank you to our presenter, Paul Chambers, for sharing his expertise and insights. Remember, you will be receiving a follow-up email with the resources discussed today, so keep it on your inbox. We appreciate your participation and engagement. If you enjoyed this session, we invite you to join us for our next one, where we'll be exploring the aspects of the basic CO2 system. If you want to circle back on the information that we have today on our presentation, navigate to our Sportland YouTube page, our channel there. You'll find a library of video highlights and some of our product information. Also some basic and advanced educational topics. So we just thank you again, and we will see you.